So again, as a quick, just re-going over it, because I think maybe sometimes I confuse myself. If T is a linear map, right? If T is linear, and linear means we have alpha x plus beta y for some alpha and beta and something. It doesn't matter what it is, whether it's part of R or but usually if we're doing derivatives and stuff, we would want it to be just part in Rn. Then we have that this is equal to alpha of x plus beta of y. And in the standard basis, if T is a linear, then we can find a matrix, right? Matrix such that T of x equals ax. And so if T was going from, T is a function going from Rn to Rm, then A is a matrix going from, so it's an, I think it's an m by m matrix, or m, let's see, so we want it to be, because x is n by 1, so we want it to be m by n, so we want A to be m by n, okay? Okie doke. And so what's next? Yes, so we're going to define the derivative, and then we'll check indeed that if we put in t, then the derivative of t should just give us back t, right? Because earlier we said f, I mean, I don't know, it's kind of redundant, but we said f of x equals t of x, and then we did that. I kind of explained that it should give us that, with the analogy to the one-dimensional case, the derivative at a point x of the function f should give us t. And so we see that in fact, indeed, the derivative is a linear map, and in the case that the original map is linear, the derivative would be itself. Okay, so in fact, if t is linear, derivative t of x equals t. Okay. Okay. So this is something we'll check, and then let's first write down the definition. Finally, let's write down the definition. So the definition of the linear map is, a derivative as a linear map is, we have that d f of x. So if we have a function, so start with if, we say a function from Rn to Rm is differentiable if and only if, so their definition, there exists a linear map, a differentiable at x, okay, differentiable at x, okay, at x in Rn, if there exists a linear map such that so we have f of x plus v. Okay, so v is also in Rn, and so we kind of want v to be a small number, is equal to f of x plus d of x of f at v, so the linear map evaluated at v, plus some function r of x and f evaluated to v. Okay, and so this r is just a remainder term, so whatever's left over when we subtract these two from this, we'll call that r. And we want r to have the property that that as v goes to 0, as you put it like an epsilon ball that v has to be contained in, you can find for all epsilon greater than 0, you can find a delta ball, so that if v is inside the delta ball, the magnitude of this term is less than epsilon. So that's like the epsilon delta definition. So basically, if v is small in magnitude, we want this to be small in magnitude. So let's say that for all epsilon greater than 0, there exists delta greater than 0, such that if the absolute value of v, so this v is a vector, is less than delta, then r of f(x) v and the magnitude of this is less than epsilon times the magnitude of v. Okay, so the idea is that the error term is decreasing faster than linear, right? So we can make this epsilon as small as we want as long as the v is sufficiently small. Okay, so this is a definition, and let's actually confirm this as a theorem, and we'll do that in the next video.